Okay, so what we have here is a pretty typical problem of the method of Lagrange multipliers. So we want to find the minimum and the maximum of the function xy on the ellipse x squared plus 4y squared equals 8. So this is what we call the objective function. And this is the constraint. So what we want to do is create a function that has a level set which coincides with a constraint. So we want to write down a function such as x squared plus 4y squared minus 8. Usually you can take everything to the left-hand side and create such a function. And once you have that function, the method of Lagrange multipliers tells you that the critical points of the objective function are where the gradient of the objective function is parallel to the gradient of the constraint function. And you also want to make sure that whatever points you find satisfy the constraint. So this is the system that one has to build. Okay, let's see how all this applied in our case. So what we would like to do is begin by defining. So we define g of xy to be x squared plus 4y squared minus 8. And then the system that we would like to solve is that the gradient of f is lambda times the gradient of g, lambda being the usual auxiliary unknown in the method of Lagrange multipliers, and g is equal to 0. Okay, let's see how this translates into simple equations. So first of all, the gradient of f is y comma x, y being the partial derivative of xy with respect to x, and x being the partial derivative of xy with respect to y, equal to lambda times 2x 8y. And of course, the equation g equals 0 is x squared plus 4y squared is equal to 8. And this translates to y is equal to 2 lambda x, and x is equal to 8 lambda y. And x squared plus 4y squared is equal to 8. So now what we do here is simply argue that none of the numbers x, y, or lambda can assume the value 0 if they're part of a solution of the system, right? So let's explain that. Why can't x be 0? If x were 0, then the first equation would imply that y is 0. And then if you have both x and y being equal to 0, they would never satisfy the constraint equation. For the same reason, y cannot be 0, because the second equation would imply that x is 0. And so the constraint would not be satisfied. And finally, if lambda was 0, then by the first two equations, both y and x would be 0. Again, not a possibility. Why are we making this point? Because now we can take the first equation and divide it by parts by the second equation. This is possible only if you know that the denominators are non-zero, which we just established. And now you have a cancellation of the lambda, which has to be non-zero, as we said. And upon cross multiplying and simplifying 2/8 to 1/4, we get 4y squared is equal to x squared. So once we know this, we plug it into the constraint. So let's say we replace x squared by 4y squared. So we get 4y squared plus 4y squared is equal to 8, which means that 8y squared is equal to 8, which means that y squared is equal to 1, which means that y has to be plus or minus 1. And let's see, so if y is 1, then plug it into the constraint equation, and you will get x squared plus 4 is equal to 8, which implies that x squared is equal to 4, which implies that x is equal to plus or minus 2. So we get 2 points from here, the points 2, 1, and negative 2, 1. And then go with y equals negative 1. Here, what you get is exactly the same because of the square. So you will get that x squared is equal to 4, which means that x is equal to plus or minus 2. And this will mean that we also get the points 2, negative 1 and negative 2, negative 1. So these are the 4 points, the 4 critical points. And we have a function defined on a compact set, meaning the ellipse. So the minimum and the maximum are guaranteed to exist. And what we do is we plug them into the objective function to see which one gives us the smallest input, which one gives us the largest input. And what do we have? So we have 2, 1, negative 2, 1, 2, negative 1, and negative 2, negative 1. So this will give us 2, this will give us negative 2, negative 2, 2. This has to be the maximum along with this point here. So the maximum is obtained at 2 places and the minimum is obtained also at 2 places. And we have all the information. So we have at what points we have the extrema and what the values of those points are. And that's it. That's all we needed to do. Thanks for watching.